I want to thank the organizers for inviting me and giving me a chance to speak here. And I especially want to thank Mladen, whose influence at the French Foreign Ministry made sure that I could get visa and come here. Okay. It's strange, but also very nice to be able to be in a room full of people without masks on. So it will get. I'll need some getting used to this. Okay, so I'll talk about Brumer-Stark units and a conjecture of Galois. So. Okay, I'll start writing a little larger after that title. Yeah, okay, sure. So one thing that all the online talks have done is, I've gotten out of habit of writing on the board one, and then things seem to move slowly on board, so which is a good thing, I suppose. So F is a totally real number field. So this will have a bunch of notation. This board. H over F is a finite abelian CM extension. I denote its Galois group by G. Okay. So for any character of G, so of course I'll not say this, write this down, but we fix an embedding of Q bar into QP bar and complex numbers and so on. So we can talk about p-adic characters or complex characters as usual. So I define the L function with, S is a finite set of places of F. S contains the places that ramify in H and all the infinite places. So I guess the notation is self-explanatory. This is the imprimitive L function with Euler factors in S removed. Okay, so a priori only for real part of S bigger than 1, and as usual it has a meromorphic continuation to C and so forth. Okay. So then we have this element, Stickelberger element, theta S H over F. A priori this is an element in the group ring with complex coefficient. What is the property? So when I evaluate this at any character of G, I get this L function, value of this L function at 0. Okay, so for all chi in G hat, let's say. Okay, and a conjecture that Broomer made, which turns out to be equivalent to a conjecture that Stark made, and then Tate kind of related the whole thing, is if I should maybe say before that right, so maybe I'll just write it here. Theorem of Siegel and Shintani is that theta S H over F is actually an element in QG. Okay, so if I take theta S H over F, all the ZG multiples of the, and look at all those that land inside ZG, this is contained in the annihilator ideal of class group of H. So ZG class group of H is a ZG module, and so you can look at its the set of all elements in ZG that annihilates it. That's an ideal. It's the annihilator ideal. And the conjecture is that any multiple of any ZG multiple of theta that lands inside ZG is actually an annihilator of the ideal class group. Okay. Okay. Yeah. Well, to hold it, you mean? Okay. Hand works better than machine. All right. Okay. So, so that statement makes sense because of this theorem of Siegel and Shintani. Sorry, what's the time? Okay. All right. So, well, this kind of thing is probably not the most ideal way of writing this. So, I'll introduce some more notation. So, this kind of is some technical stuff which you may or may not have seen kind of written in this way. So let T be a finite non-empty set of primes of F disjoint from S. And then I have some technical condition on this. So assume that T contains two primes of two distinct residue characteristic or a prime of large enough residue characteristic. So let me just assume the latter. It's either of those condition is fine. So assume that T contains a prime of residue characteristic bigger than degree of F over Q. I think that's sufficient. So I denote the, so you modify your L function with another decoration. So this is Ls chi S times all places in T 1 minus chi of V norm of V to the 1 minus S. So this is just some finite product that you multiplied by. It doesn't change the analytic properties of your L function very much, but it does something nice for theta, the modified theta thing. So this is an element in CG such that chi of theta st h over f is Ls t chi inverse 0. Okay, and what this does is you get the following theorem due to Casaunokas and Deligne-Ribet, which says that this is actually an integral element. So theta st h over f is in ZG. Okay, so you can restate the conjecture by saying, so this is Brumer-Stark Tate, theta st h over f belongs to the annihilator ideal of actually something bigger. So let me write it down and then define it on the next board. So it actually lies in the annihilator ideal of something bigger. And what is this bigger thing? So you take all the okay, non-zero ideals co-prime to T and then mod it out by non-zero principal ideals which are congruent to 1 modulo all primes in T. So that's the way I'll write it. What this means is you're taking, so in terms of class field theory, this corresponds to extension of H, which is unramified outside T and at most tamely ramified at primes in T. Okay, and so the usual class group is a quotient of this, and so this is annihilating something bigger, so it does annihilate the class group. And so this thing is known away from 2, so that's one of the results that Samit and I proved, that theta st h over f, this belongs to the annihilator ideal over CLT H tensor Z half. Okay. So we prove it away from p equal to 2. Okay. All right. So this is not, I'm not going to talk much about this theorem today. So we'll see a corollary of this. Yeah. Let me just sort of say that at 2, it's not just merely technical. I think one needs new ideas apart from what we do to prove this at 2. So yeah, the extension to p equal to 2 is going to be non-trivial. That's my guess. Okay. All right. So I want to talk about a corollary of this, which gives us existence of these Brumer-Stark units from the title. So let me say what I mean. So again, what I do is I fix an odd prime p from now on. So fix a prime number p not equal to 2, and and p in f above p, and you also fix a such that p splits completely in H, okay, and you fix capital P in H above your small p. Okay.
So clarify this LST, you're adding Euler factors at 1 minus S at T or at S? Or at S minus 1 at S? You do a 1 minus
No, yeah, this is 1 minus S. Yeah. It's okay. Yeah, I mean the more classical way of stating this theorem of Cassavant-Augustin Deligne-Ribet is that if you take the number of roots of unity in H and multiply your theta s by that, then you get something integral, and these factors are precisely the one that whose GCD is divisible by the number of roots of unity, and with these technical conditions it is precisely equal to that. So all right, so what do I want to say next? Yeah, right, so let me put U to be set of all x in H cross such that the absolute value of x at W is 1 for all W not dividing P, and this is including, not dividing P, this is including the Archimedean places, okay. So I don't need to write it, but this is including the Archimedean places. of H. So one of the corollaries, which is how Stark stated this conjecture, is the following. So there exists U, P in U, such that the following happens. So what I do is I take, right. Okay, let me write it in a couple of different ways. First, let me write it in the group ring form. So I define ORD sub G of UP. So this first equality is just the definition. This is all, this is sum over all sigma in G ORD at this fixed prime P of sigma U, UP, sorry, chi, no, sorry, sigma inverse. So this is an element of the group ring, and what the content of the corollary is that this is equal to, sorry, I have one more condition here, yes. Sorry. X is congruent to 1 modulo all places of H which are above T. Okay, so I'll simply write it that way. So this is theta S T H over F. Yeah. So that's the, so this is the content of the corollary, and this is the thing. If you want it to be written more sort of without the group ring thing, then what this means is that chi of ORD G U P is equal to summation sigma in G ORD P sigma U P chi of sigma inverse. This is equal to L ST chi inverse 0. Okay, and the way to prove this corollary is simply by sorry? Yeah, that random set that we have fixed. Yeah. So P, yeah, so P does not belong to, yeah, you just have to stay away from P. Yeah. Thanks. Right, and the way to prove this from the theorem, so is, so yeah, I think, right, I'll ignore that we don't know the theorem at 2 at some places, okay, even though I said it's non-trivial, it's just to make it expositionally easier. So ideally I should write UP in U tensored, yeah, sorry, so huh? This one?
No, you put like an or. You have both, right? It's not like and, no?
No, these are equivalent ways of stating the two things. Yeah. No, I mean, or equivalently stated.
Right.
Yeah. Oh, yeah. Yeah, that's, sorry. Thanks. Which is same as saying this holds for all chi. Okay. Yeah. Okay. Yeah. So right. So I mean I have to, so to say that I get this, I have to tensor everything by Z1 over 2. All right. So. But in the proof, I'll kind of ignore this, and I'll just say that you look at the class of P inside CLT of H, and then we know that P to the theta ST of H over F, this is some, this is a principal fractional ideal generated by an element which is which has valuation 1, I mean which has norm 1 away from primes above P, and it is congruent to 1 mod t. Okay, so this is how you get your UP from the theorem. Okay, so this UP is called the Brumer-Stark unit. Okay, so this is what we are interested in, and so it's odd at primes above p is related to these L values, and the other interesting property is that these UPs, they generate abelian extensions of f. So if you vary p and you vary your h, and then you get all possible abelian extensions of f in some precise way, which I'm not going to say today, but they give you abelian extensions of f. Okay, so that's one important property that they have. So when f is equal to q, these UPs are, this UP is a Gauss sum. Again, I'm not going to write down what exact expression it has, but it is Gauss sum. So these are the ones that Stickelberger uses to prove Stickelberger's theorem, which is this thing is a generalization of Stickelberger's theorem, right, when f is equal to q. Okay. So these UPs are kind of important algebraic numbers, and we want a formula for this. So question, how to construct these UPs explicitly. Right? As you can see, this is just an existential statement, because unless we know how to calculate what this ideal is explicitly as a principal fractional ideal, we wouldn't know how to construct UPs explicitly. So more precisely, you can ask the following question. So this thing is in H, which is contained in H P, which is same as Fp star. So what is this element? Okay, so what is UP as an element in Fp? Okay, so can we write this down explicitly? Okay, so let's see. And so this is a conjecture that Darmo and Dasgupta made when F is a real quadratic field, and then Dasgupta made in general, and there are various avatars of this due to Charlois, Dasgupta, and Greenberg, I think. So Matt Greenberg. Okay, so let me say this in the form that Dasgupta made in, I think, about 2008. So what he did was he constructed and I'll say a little bit about how this measure is constructed. Constructed a z-valued measure, let me call it nu, and it depends on some choices. So A, S, T on. So for this, let me actually say that I'm going to, I'm going to do this in a very special case. So, so assume, so this is just for expository requirement. So P is inert in F, okay, and so This just makes things easier to write down. This is not required. This is not necessary for what's done. So on O, and I just didn't. Okay, maybe I'll denote it like this. Okay. So I'll say a word about how this measure is constructed. So A is an integral ideal co-prime to S, T, and also P. Okay, so just some auxiliary choice of integral ideal which is co-prime to everything. Okay. Of F, yeah, integral ideal of F. Yeah, thanks. Okay, and then the conjecture is that I'll say what this is UP. So it not only gives the formula for UP but all its conjugates, Galois conjugates, and so this is P zeta S union P comma T. I'll say what this is. Sigma 0 no, this is not. This is simply S comma T. Okay, I'll say what this is in a minute. This is some multiplicative integral in the sense of Darmo, but d nu a s t. Okay, and for later use, I'll denote this quantity by sigma up analytic. So this is just right. So we want to show that the conjugate of the Brumer-Stark unit is same as this analytic quantity that's defined, this p-adic analytic quantity that's defined, and this equality is in FP cross. Okay, so the conjecture is this p-adic quantity which a priori lives in FP cross is an algebraic element and it's equal to the Brumer-Stark unit. All right, so what are these things? So this is ST H over F. This is an element of the group ring, so I can simply write it as sigma in G zeta S comma T sigma 0 sigma inverse. Okay, so these are these partial zeta functions. Partial zeta values. Okay, so these are these quantities here, which is not surprising. So this will turn out to be a unit, and this is what the odd at P is.
This integral is just the first moment of the measure?
Yeah, because it's just x, yes. Oh, right. Okay. So I have to tell you something about the this measure now. So this is done using the Shintani formulae for partial zeta function. So I'll write down only very briefly how this measure is defined. Okay, so maybe I did not say this. So n is the degree of f over q, and these are in Rn, the positive orthant of Rn. These are linearly independent. Okay, so I just take any independent over R, and I just take the Ci V1 up to Vr. This is simply the the positive linear combination of such things. So Ti, Vi, okay, these are real numbers. So this is what is called a fundamental. This is yeah, so some simplicial cone. And now I have to figure out how to do this. Okay. Only happens one by one, I suppose. Oops, not this one. Okay. Okay, I don't. Should I use this or this? Okay, let me try use. Huh? It is wet. Should I use this or? No. Okay. Don't. That's a clear answer. I like that. So. Sorry? Maybe I shouldn't use. I don't know. Should I use that? No, I'll just use this. Maybe I should erase this with the wet thing and then use the two empty blackboards and let this dry. Okay, anyway, so okay, so I'll define something which just very briefly. So for real quadratic fields, for which you may have seen Shintani's formula, because things are easier there. In general, you have to take kind of signed linear combination of such simplicial cones. So I'm going to state a result which is due to Colmez, but in this form I think is Galois, Dasgupta, and Matt Greenberg, which says that there is a nice choice of what is called signed fundamental domain, which I'm going to say what it means for action of yeah. So okay, let me say n is the conductor of or discriminant of H over F, whichever way you want to define it. So E n, these are all units in this such that X is congruent to 1 modulo n. Okay. So En acts on the positive orthant, and you look at the fundamental domain. So there is so this is not a technical term. I just don't want to say what kind. There is a very explicit form of what is called a signed fundamental domain. So you write something down and then you show that that's a fundamental domain. So I'll say what fundamental domain means for linear combination of simplicial cones for the action of En on this positive orthant. So fundamental domain D, and this is some. So D is some linear combination of such simplicial cones. So this is a finite linear combination, I going from 1 to some k, and these AIs are integers. what this means is that summation u in En summation I ai with the characteristic function on Ci, so that makes sense, with u acting on x. This is simply the identity function on this. How do I denote it? Yeah. Okay, so that's what it means to be a fundamental domain. And so you have action of this on this, and you can write it. You can write down a fundamental domain in terms of simplicial cones. But here you allow them. You allow Z linear combination of that. Signed because these are not just union of simplicial cones. This is more. Some come with sign like minus of an integer, minus of a positive integer. Yeah, these are not necessarily positive integers in general. Okay, then you can write down a partial zeta function sort of thing. So a u. So u here is a is an open compact inside this. So I want to define a measure, right? So I have to take it on such things. So you take all those things which lie in A inverse n plus some z. So this will be kind of evaluated at z. And yeah, what am I? So let me just write this. I can't figure out what I put. So alpha and s are co-prime. Norm of alpha to the minus s. Okay. There is no t in this formula, right? Yeah, there is no t because t. Yeah, there is no t. So yeah, thanks. So t is going to come a little bit later. Yes, thank you. But it depends on what choice of d I make, I think. Yeah. So something like this. Okay. So t will come later. What I'm going to do is I'm going to take t to be a singleton element with large enough residue characteristic. Okay, maybe even inert if I want. So then my new A S T evaluated at u will be this thing minus L zeta A L inverse. So I said integral ideal, right? Here I also want 0. Yes, thank you. What I was worried about is I said integral ideal, right? So where did that go? Oh, okay, I don't want to change it up there. So, yeah, non-zero ideal, I think, because this thing otherwise wouldn't make sense in the things that I have defined. Okay, so this is the measure. This is the kind of measure. So if you if you consider this, then what's happening is you are taking the sum over a fundamental domain rather than in a quotient group, and we know that this kind of doesn't. This depends on these choices of this depend on the choice of this fundamental domain, but its value at 0 does not depend on the choices. So this is the kind of thing one uses, and this is the kind of thing that Shintani does also. So okay, so that's the nature of this formula that Dasgupta can. Yeah.
What is Z in this sentence?
Yeah. What is yeah, I forget what Z is now. All right, let's. What did I write? Yeah, my notes don't seem to say what Z is. So sorry, I'll write that when I figure it out. Sorry. So no, it's some complex number, but I think so. The value at 0 kind of makes sense. So yeah, sorry, I should have written better notes. Okay. Anyway, so the yeah, I'll say that in a. Yeah, so Pierre would know this. How is the anyway, I'm not sure. I'll let this be as it is, because if I try to change it, I'll make a mistake. So I'll let this be. Okay. So what is our approach into this this conjecture of Dasgupta? So we kind of solve a completely unrelated looking thing to actually prove this conjecture. So let me come to that now. Okay. So this next part will look very different from what we have up to now. So this is called the tower of field conjecture of Gross. So this is the second part of fields conjecture of Gross. Okay, so let me write S prime to be S union this extra P that I had, a prime of F which splits completely in H, and I take another field which is above this. So let me call this script G. This is G. This is gamma, and then L over F is again L over F is abelian and unramified outside of S prime. Outside of S prime. Okay, so you do allow ramification at P, and this is important. So you have this augmentation map from ZG. This is called the relative augmentation map. So any element here in script G projects to the usual G, and you just extend it Z linearly, and I be the kernel of this. So if you look at theta S prime T, but for the bigger extension L over F, then this in fact lands inside I, because if you take the augmentation of theta S prime T L over F, then this is equal to theta S T H over F multiplied by 1 minus the Frobenius at P, but this is 0. Okay, so this thing is 0 in ZG. So you get that this is actually in the augmentation ideal. So let me just remark here without writing anything that if instead of taking one prime that splits completely in H, if you take R primes of F that split completely in H, and your S prime is S union those R primes, then Gauss conjectured that the corresponding element actually lives in the rth power of this augmentation ideal I, and that's much harder to prove. Okay. So it has a, so this is like saying this theta has a 0 at this theta has a 0, right, at s equal to 0, and if you have R primes that split, then that theta has a 0 of order R, but that's much harder to prove. So so there are two proofs. One goes via main conjecture, so that's due to Wiles, and another that's purely p-adic analytic due to, again, Galois, Dasgupta, and Greenberg. Okay, so this is one side, and then on the other hand, you have a map, the local reciprocity map, from H sub p into gamma. So this is reciprocity map, and using this I define. So again, I think I'll use this. So let me, just like the OR thing, let me write this. So the first thing is the definition. So again, you take sigma in G, and you take so let me this sigma u sub p minus 1. So this is an element in gamma, and I'm taking minus 1. So this thing lives inside the augmentation ideal, sigma tilde inverse. So this is an element in I mod I square. So this is well defined only in I mod I square. So what is this sigma tilde? Sigma tilde here, sigma tilde is a lift of sigma in G. So any lift, okay? And because I am taking this in I mod I square, this is independent of the lift that I am taking. Okay, and so the tower of field conjecture that Gauss made is that right, so theta s prime t L over f, this is equal to this in I mod I square. Okay, so that's where it's kind of defined. Okay, and yeah, so the theorem that we prove is that, again, this holds away from p equal to 2, and you only have to look at p-adic things. So so theta s prime t L over f, this is equal to in I mod I squared tensored with ZP. So remember, P is odd. Okay, again, we don't know what to do at P equal to 2. Yeah. Okay, so what does this have to do with the previous conjecture? So let me come to that now. by the way, before saying all that, I should make this remark here. So Bullock, Burns, Dowd. So this is David Burns, and Dominic Bullock and Alex Dowd are his students, and Sugil Seo from Seoul. They proved some case of ETNC. So ETNC for GM and totally real fields. Okay, so minus part of, these are just some words if you haven't seen. So minus part of ETNC over F, and so this implies, so this uses, so using the thing that we proved is strong Brumer-Stark conjecture. Okay, and this again implies this theorem and something slightly more general. So implies the conjecture in I mod I squared tensor Z1 over 2. So this is slightly more refined than what we do. But the main ingredient there is this strong Brumer-Stark conjecture. That was a refinement of the first theorem I stated. Okay. So what does this have to do with relation with Dasgupta's conjecture? Okay, so the relationship is somewhat sort of complicated to do, but it basically says that you take an appropriate infinite family of this tower of field conjecture, and that implies Dasgupta's conjecture. Okay, so let me say how. So Fs prime, this is maximal abelian extension of F unramified outside of S prime, and this is what I mean, I never said that. Did I say L was finite? Yeah. So actually L could be an infinite extension here. I should just work with completed group rings in that case. So so Z double bracket G. So this is what I'm going to do, or you can work with finite extensions of F which are contained in this and then and contain H and then pass to an inverse limit. So it's the same thing. Yeah, you could choose different L's, and you could even choose different S. That's the idea.
But you still serve you the same answer.
Well, I mean, it's in different I, right? Even I changes depending on what. Okay. Okay, then so I'll be very brief here, and so Galois group of Fs prime over H. This thing is O star mod En. This is topological completion of that. So what is O star? O star is, or maybe I should have written O cross, right, as writing. Okay, anyway. So V in S prime minus S infinity U V n. And what is U V n? This is all So this is the usual sort of higher principal units. These are x in OV cross such that x is congruent to 1 modulo n OV. So if this is the whole thing, then there is no condition on x, and it's just OV star in that case. Okay, and then you embed this diagonally in this and take its p-adic closure or v-adic closure, sort of various v's. Okay, so okay, let me be brief here. So what Gross's tower of field conjecture. So this is some involved computation that one has to do, but not very hard. Tower of field conjecture implies that so there are a bunch of kind of components here. Okay, so except in P, you kind of take. So what is sigma A? This is the Artin symbol attached to the ideal A, and this is UP. So this is the component that you take in the So this I write as OP cross everything else, right? So there's OP here, which I just for simplicity I take that to be the first component for writing these things, and then you take one here. So you can show that this is actually equal to the quantity that you want to show in sigma A 0 in Dasgupta's conjecture. So this is the big O cross. So you can extend this construction of Charloha, Dasgupta, and Greenberg to whole of this O, not just in the first component, and you can do this thing. So let me this is the thing. So this we kind of denote. I mean, this is why I had the notation earlier. So sigma A UP analytic, right? So if you do this kind of thing with other components, you get 1 1 1, and Gross's conjecture implies that this is equal to this, but now not in OF, okay, but in some O cross modulo E n bar, because that's what that is what this gamma is, right? This was the gamma. And so let me remind you what's the relationship with I mod I square and gamma. So I mod I square is isomorphic to gamma tensored with ZG, right? So you have some equality in I mod I square, and from that you get an equality in gamma, which is what Gross's conjecture says, whereas Dasgupta's conjecture says that actually this equality should hold just in O star, not modulo, yes, okay, this equality should just hold in O star, not modulo En, right? So now what you do is you change your set S, in this, I mean, so sorry, in the last part, N is actually sort of the discriminant of H over F times product of V in S, V unramified, V in S prime. So you not only include primes in that are ramified, but also primes that are unramified. And so what you do is you take your S prime to be bigger and bigger, so that this thing becomes smaller and smaller. So you get this equality. You approximate it with something in O star. So this is what is, I mean, you use Taylor-Wiles kind of trick to go from this quotient to O star itself. Okay, I'll stop here. Thanks for going over. Sorry for going over time. Thanks.